The exploration and potential realization of a highly sophisticated, technologically advanced framework for conducting operations within the space environment represents a paradigm shift that could fundamentally alter the methodologies by which spacecraft are deployed, managed, and maneuvered, particularly within the gravitational influence of Earth's orbit. This forward-looking initiative is concentrated on the conceptualization and eventual construction of what is being described as an orbital carrier. This envisioned structure would not be a transient object but a persistently stationed platform, likely residing in low Earth orbit, operating under principles analogous to terrestrial naval aircraft carriers, yet uniquely adapted for the vacuum and microgravity conditions of space. The core design philosophy for this space-based edifice would be to equip it with the capacity to house, securely store, and, crucially, launch a variety of smaller spacecraft. These could range from compact satellites for communication or observation, to highly agile, maneuverable space vehicles designed for specific tactical or logistical purposes, all deployable precisely when and where they are needed. This operational model stands in stark contrast to the prevailing contemporary methods, which predominantly depend on launching individual satellites from terrestrial launch sites each time a new asset is required in orbit. Such ground-based launches are notoriously complex, demanding meticulous scheduling often months or years in advance, incurring substantial financial costs for each mission, and necessitating intricate logistical coordination involving multiple agencies, launch providers, and ground support infrastructures. An orbital carrier, by its very nature, would aim to circumvent many of these inherent time delays, reduce the per-deployment resource expenditure, and offer an unprecedented level of responsiveness by having assets already in space, poised for immediate activation and deployment. The intellectual genesis of such a carrier concept is deeply intertwined with the escalating complexity and the perceived growing urgency associated with space as an operational domain. Space is no longer viewed solely through the lens of scientific inquiry or peaceful exploration. It has inexorably evolved into a sphere of significant strategic interest, and by some accounts, a contested environment where factors such as timing, precise orbital positioning, and the capability for rapid reaction are becoming increasingly critical determinants of operational success and strategic advantage. An orbital carrier could, therefore, function as a pivotal enabler, facilitating significantly faster and more agile responses in orbit. This enhanced responsiveness could manifest in various ways, including the swift repositioning of existing satellite assets to meet emerging needs, the rapid deployment of observation or communication relay satellites to cover dynamic events or fill coverage gaps, or potentially, the ability to counter perceived threats originating from the space assets of other nations or to mitigate hazards posed by orbital debris or malfunctioning satellites. Gravitics, Inc., a commercial entity specializing in the development of space-related infrastructure, has reportedly been engaged to contribute its expertise to the developmental phases of this ambitious project. This endeavor is also receiving support from SpaceWERX, which serves as an innovation-focused division associated with the United States Space Force. While the comprehensive, long-term financial implications of designing, assembling, deploying, and maintaining such a complex orbital structure are still largely undetermined and subject to considerable analysis, the project has received an initial allocation of potential funding, reportedly up to $60 million, designated for early-stage development support and feasibility studies. This level of financial commitment, even at this nascent stage, signals a serious intent to advance this complex, yet potentially transformative, paradigm for future space operations. The preliminary technical schematics and conceptual designs for this carrier are understood to incorporate features that would enable it to pre-position a diverse fleet of maneuverable spacecraft within the orbital environment. These subordinate vehicles could then be dispatched as dictated by operational requirements, to respond to emergent threats or dynamic situations, or to provide support for other ongoing or planned missions, all without the inherent delays, atmospheric transit risks, or extensive ground preparations associated with launches originating from Earth's surface. The physical assembly of the orbital carrier itself would likely necessitate a phased construction methodology, mirroring the complex, multi-stage processes successfully employed in the construction of large-scale orbital structures like the International Space Station. The ISS, for example, was not delivered into orbit as a single, monolithic entity but was meticulously built piece by piece over an extended period, involving the coordinated efforts of multiple international partners and dozens of separate launch missions. A similar modular construction approach would almost certainly be anticipated for an orbital carrier. This would involve various structural components, advanced propulsion units for station keeping and maneuvering, sophisticated docking ports for receiving and dispatching smaller vehicles, and complex life support or robotic maintenance systems being launched individually from Earth and then painstakingly assembled in the challenging environment of space. Consequently, the realization of such an orbital carrier is less about launching a singular, albeit large, spacecraft, and more akin to undertaking a major infrastructure construction project in orbit. Such a project must meticulously account for a myriad of engineering challenges, including the immense weight of components, the substantial fuel reserves required for orbital maintenance and operations, the potential need for life support systems if the platform is to be crewed or periodically serviced by human astronauts, and the critical importance of ensuring long-term structural integrity and operational durability in the harsh, unforgiving conditions of space, which include radiation exposure, thermal extremes, and micrometeoroid impacts. The potential utility of an orbital carrier could extend significantly beyond the mere rapid deployment of assets. By stationing a diverse array of vehicles in orbit and providing operators with the capability to reposition, reconfigure, or activate these assets directly from the space-based platform itself, the carrier could evolve into a multifaceted, floating logistics and operational hub. One can envision it functioning simultaneously as a maintenance and refueling depot for smaller spacecraft, a sophisticated command and control center for regional or specialized space operations, and potentially, a platform for deploying surveillance assets or even defensive systems. It is not a far-fetched extrapolation to imagine a future scenario where multiple such carriers are strategically positioned in various orbits around the Earth, each configured with a unique complement of small satellites, reconnaissance probes, communication nodes, or other specialized payloads. Each carrier in such a network would be maintained in a state of readiness, capable of initiating actions with remarkably little advance notice. Compared to current timelines, this would grant an unparalleled degree of operational flexibility and strategic leverage to the entity or entities controlling such a system, particularly in time-sensitive scenarios where critical decisions and responsive actions must be executed within hours or even minutes, rather than the weeks or months typically required to plan, prepare, and execute a traditional Earth-based launch. Nevertheless, a host of significant and complex questions remain unanswered regarding the long-term sustainability of such an orbital system. These include how it would be effectively shielded or defended from the ever-present threat of orbital debris, how its complex digital systems would be protected from cyber vulnerabilities and malicious attacks, and how its operations would align with, or potentially challenge, the existing framework of international space law and established norms of behavior in space. Furthermore, profound questions concerning national sovereignty in space, the potential for such a capability to be perceived as an escalatory step in the militarization of space, and the consequent risk of triggering an accelerated arms race among spacefaring nations could prominently emerge as other countries observe and react to the development and deployment of such a potent new capability. While the concept of an orbital carrier is still situated in its conceptual and early developmental stages, the underlying strategic message being conveyed by its proponents is unambiguous. Space is increasingly viewed not merely as a realm of scientific discovery and boundless possibility, but as a vital, strategically significant, and potentially contested frontier where attributes such as speed, operational readiness, and profound flexibility could decisively shape the balance of influence and security in the coming years and decades. The chief executive of Gravitics has reportedly underscored the potentially revolutionary nature of this project, articulating it as a means to fundamentally dismantle the traditional barriers and constraints associated with space launch, thereby empowering mission operators with the unprecedented ability to select and achieve desired deployment orbits with remarkable speed and dynamic adaptability. This vision implies a radical departure from the established paradigms of fixed launch windows, constrained by celestial mechanics and range availability, and pre-calculated, relatively inflexible orbital insertion trajectories. Instead, operators would be interacting with a persistent, orbiting platform, continuously primed and ready to launch its diverse payloads to precisely targeted orbital locations and at times dictated by immediate operational necessity. Such a capability could potentially revolutionize how nations maintain their presence in space, conduct vital surveillance and reconnaissance activities, or respond to natural disasters, humanitarian crises, or security emergencies occurring both on Earth and in orbit. In purely practical and economic terms, although the initial investment required to design, develop, launch, and assemble such an orbital carrier will undoubtedly be substantial and fraught with complexity, it is conceivable that it could offer significant long-term cost benefits. These benefits might accrue from a reduction in the frequency of expensive individual ground launches, the potential for on-orbit servicing and upgrading of assets, and the creation of a more efficient, responsive, and sustainable infrastructure in Earth orbit. However, transcending the purely economic considerations, this concept is fundamentally about redefining the very essence of what it means to operate effectively and persistently in the space domain. It signifies a shift away from a model characterized by a series of discrete, often isolated missions launched from Earth, towards a future characterized by an integrated, interconnected network of orbital assets capable of a high degree of autonomous function, rapid, coordinated action, and enduring, influential presence. Whether or not this particular vision of an orbital carrier materializes exactly as currently envisioned, the serious consideration, discussion, and preliminary development of such a concept powerfully highlights the accelerating transformation in how space is perceived and utilized, evolving from a distant frontier to be reached, into a dynamic domain to be actively inhabited, managed, and strategically leveraged.